In today's lecture, I'm going to talk about Hermalin's paper on leadership. This paper exploits the team production model of Holmstrom that we studied earlier and uses that framework to talk about leadership. Now, of course, leadership is very important in organizations. So there's a general notion around that, organizations which lack good leadership do not succeed. Uh, and the idea of leadership or what constitutes good leadership is, of course, very rich and diverse. So this paper just focuses on one aspect of leadership, and it offers us an informational theory of leadership. The idea is that a leader is a leader by virtue of some special information that he or she possesses. So to start with, let me show you these three little quotations which illustrate some aspect of the idea that is developed in this paper. Right. So the first quotation says that the key to successful leadership today is influence, not authority. So you can think of very strong leaders who lead by brute force. For example, emperors and kings who keep everybody in line because of coercive power that they have. But if you're talking of leadership, let's say in modern organizations like a company, right, leadership offered by the CEO or the top management, there people have to be persuaded to work to act in ways that the leader wants them to do. Right, the leader cannot do it by brute force. So influence is key to good leadership. The second quotation says a good leader, a good general, not only sees way to victory, he also knows when victory is impossible. So a good leader has good news as well as bad news and can perhaps convey that to the team to course the chart to chart the course, of the team and how people should act. And finally, this Chinese proverb says that not the cry but the flight of a wild duck leads the flock to fly and follow, right? So the basic idea there is that leaders influence through actions, not words. Okay, so let me jump to the model. We will work with the same team production function that we saw in the Holmstrom paper, right? So team output is given by theta, some productivity parameter, times the sum of everybody's effort. The new innovation here in this paper is that the productivity parameter theta is a random variable. So the team could be highly productive or could be less productive, and there's some uncertainty regarding that. To keep the math simple, I will assume that theta is uniformly distributed between 0 and 1. Right? Nothing really depends on that. We can easily extend the results to general distributions. We'll also take that agents are symmetric to focus on leadership related issues and not get distracted by asymmetric situations. So lambda I, lambda j, which is the cost parameter, for all agents it is 1. Now, in this situation, to set a few benchmarks and understand certain intuitions, let's focus on the value of information first. So the surplus of the team, or the expected surplus of the team, is higher when agents know what the realization of theta is compared to a situation where they don't know, where they only know that theta is this random variable, right? So take the case of full information about theta and compare it with the situation where the team members don't know what the realization of theta is. In the former case, the team surplus, expected surplus of the team will be higher. And the basic idea there is fairly simple, that when agents know team productivity, the value of theta, they can customize their efforts to the true state of productivity. So when the team is very productive, they can increase their effort and work hard and take advantage of that. But when the team is less productive, they can save on their effort and thereby save on the cost of effort. So first, let's focus on the full information situation. Theta is realized, every team member learns what the value of theta is, and then she chooses her effort level, right? Now, we are still going to calculate the expected surplus at an ex-ante stage. So when they choose their efforts, they have already learned theta. But when they're calculating the surplus for the team, at that point, they haven't yet learned theta. So we are going to take expectations over all possible values of theta. Think of this as a calculation related to a situation where, the team engages in this production every month, and every month a new value of theta is realized. So in the long run, what will be the average surplus generated by the team? That's what we're trying to calculate. Okay, so S superscript F is the full information social surplus, and that's given by this expression. Theta squared is going to be, remember that when theta is known before effort choice, the optimal effort choice of each team member is going to be theta divided by n. Okay, and that's assuming equal shares. So the total team output, the total team effort is going to be theta, and multiplied by the productivity parameter itself, theta's another theta, and so the total team output is going to be theta squared, and this is the total cost of all the team members, right? Again, remember that each of them is supplying theta divided by n amount of effort. So this is the total surplus of the team if you integrate over all possible values of theta. And when you do the calculation, you get this expression. It's a function, obviously, of n, the number of players who can supply their effort to the team production function. Now, we want to contrast that with the limited information scenario where the team members don't learn what the value of theta is before they choose their effort level. So in that case, they have to choose one effort level, right? No matter what the value of theta is going to be. And what is going to be this common effort level under the shroud of ignorance about theta? Well, it's given by the outcome of this maximization problem, right? If you look at it from the perspective of a single member of the team, this second term here is the cost of effort, right? And the first term is the share of output that the team member gets from his own effort, right? The team, this agent actually gets more than this output because others are also supplying effort, but those are independent of his own choices, right? So from his own effort, this is how much he gets. And from that, he's subtracting the cost of effort. So he's maximizing this by choosing his own E. And when you solve that problem, write down the first order condition, you get 1 over 2n to be the optimum choice. One way to understand it is that, when theta is unknown, the expected value of theta, expected productivity is half. So you have that divided by n to be the optimal effort choice for an individual. So once we have solved for this, we can plug it back into what was being maximized, and that gives us the social surplus. Well, what was being maximized times n, because that is the total social surplus. And once you do that and do the calculation, you get 1 over 8n, right? And now if you subtract this object from what we calculated in the previous slide, this difference is the change in social surplus that arises if information about theta becomes available, right, before effort choices are made. And if you calculate this difference, you can check that it is strictly positive, right? So again, all of this is to illustrate the very simple thing that if team members could choose their effort after learning what team productivity is, then welfare will be higher, right? Because they can work harder on days when the team is more productive, and they can cut down on their effort cost on the days when the team is not very productive. And so there's a value to such information about productivity. That's the key point that is being made here. Okay, now let's get to the issue of leadership, right? According to this paper. So suppose that one agent among the team, L, is privately informed about the true value of theta. So nobody else knows what the realization of theta is, but our leader, who's one member of the team, gets to know it in advance, right? And that is what sets him apart as the leader. That is the fundamental advantage which this agent has. You could think, to have a story to go along with that. Suppose that the Indian team has traveled to Australia to play a cricket test series, and the captain of the team is somebody very experienced like Virat Kohli, but the others are new, young players. They have never gone to Australia. They're not familiar with the pitches and the conditions. So the other members of the team are not very sure about what the prospect of the team is on this tour, right? Whether they can win even if they work hard. That is something that is a question mark on their minds. But the captain, Virat Kohli, by virtue of his long experience and many previous tours, he has some idea. He has a good idea about the prospect of the team. Of course, if the team gives up and doesn't practice very hard and try hard enough, then they will lose for sure. The doubt in their minds is whether they can win even if they put in their best effort, right? So mathematically speaking, relating it to this model, they are unsure about the value of theta here. Okay, so information is the true source of leadership in this model that we are studying, right? Now, as I showed you in the two previous slides, if team members remain in the dark, right, if they don't get to learn team productivity before deciding how hard to work, then that's bad for team welfare, and team welfare will improve if the leader can somehow convey this private information which he has about productivity. Yes. However, the leader has an incentive to lie, so just verbal communication won't work because it won't be credible. The leader always gets a share when somebody works harder, but the leader doesn't pay any cost of that effort, right? So the leader will want the team members to work as hard as possible, regardless of what team productivity is. Yes? So that's why even when team productivity is low, the leader has reason to exaggerate what its value is. And that's why nothing he says costlessly will be believed. So in order to credibly convey information, in particular when theta is high, in order to persuade team members that that's indeed the case, he has to engage in some sort of signaling involving costly action, similar to what you have studied in your second micro course, like the Spence signaling model, right? Some sort of costly action will become necessary. And in this paper, what we study is two forms of signaling in this sort of context. One is what Hermalin calls leading by sacrifice. So in this form of signaling, the leader sort of at the beginning makes some sacrifice, gives up some resources, either by giving gifts to others or by even burning money or throwing away some of his resources in a visible manner. And the reason for doing it is to persuade others that that team productivity is high. And the second form of leadership that will arise over here is leading by example, where the leader tries to persuade the team that productivity is high by working very hard himself and demonstrating to others that it's worthwhile to work hard. So we'll look at the details of these two kinds of signalings in sequence, one after the other. Right? And before that, let me give you a preview of what the paper shows. First of all, it shows that if we take the first form of signaling, leading by sacrifice, yes, there welfare level is restored to the level of complete information, right? So if all the team members were experienced and all of them knew what exactly theta was, there would be a certain welfare level. That welfare level is restored when the leader can lead by sacrifice, right? Effectively, the leader will be able to convey information about productivity to others who don't know it in the beginning. Equal shares remain optimal in the symmetric version. But here's a very interesting result, which we'll talk about and I'll explain. It says that if you take the other form of signaling, namely leading by example, that leads to even higher welfare than under full information. So if you compare two worlds, in the first world, everybody knows team productivity right at the outset. That's a given, and that creates a certain welfare. In the other world, that alternative world, only the leader knows team productivity. Others don't. And the leader conveys team productivity to others by through leading by example. So in the second world, where the starting information is less, right? Many team members are in the dark about what team productivity is. In the second world, somewhat paradoxically, welfare levels are higher, the team performs better, the team is more productive, right? And this is what you could call immeasurizing information, that the team is better off in a situation where the starting level of information is actually lower. And then there's a few other points which I will come to later. Right? So let me first talk about leading by sacrifice. See how leading by sacrifice works. Efforts of team members must be chosen simultaneously and privately, so they can't see each other's effort choices. The leader has learned the true realization of theta, whether team productivity is high or low or middling. Now, under this sort of arrangement, the leader must sacrifice some resources, some money, T, and must do so publicly before other team members choose their efforts, right? So before those effort choices are made, the leader can take a public action, which is giving up some money, some resources. And the amount that the leader gives up will be endogenous. That's to be kept in mind, right? And the basic idea is that when team productivity is high, the leader sacrifices more resources in order to convince others that indeed we are in a high productivity situation. And when theta is low, the amount sacrificed is lower. And the amount of sacrifice, the size of the sacrifice, is what conveys information. That's the key idea, right? What we have to find really is does this function, T as a function of theta, what does it have to look like, and try and characterize that function or pin it down so that the whole thing works. And we will take an approach here of a mechanism design approach, right? So imagine that there is some impartial, disinterested outsider who's creating this scheme, who's basically specifying a transfer function T of theta, so that it is in the incentive of the leader to convey information about theta through his choices. Okay, so we are going to focus on what are called truth-telling mechanisms. The idea is that the mechanism will specify a transfer function, and the leader will find it And what is the transfer function? The transfer function basically says the leader has to make an announcement about theta. So to distinguish the true value of theta from the announcement, we are putting a hat on top of theta, right? So theta hat is the announcement of the leader. And the mechanism says that if the leader announces the value of productivity to be some theta hat, then he has to sacrifice an amount given by this transfer function. He has to give up t of theta hat amount of money, right? And for a mechanism to be truth-telling, it has to have the property that the leader will find it optimal to make an announcement which matches the truth. That is to say, theta hat will be equal to theta for every possible value of theta, right? So let's restrict attention to such truth-telling mechanisms to begin with. Now, why are we doing that? We are doing that because of the revelation principle. So this is something which was proved by Roger Myerson, and it's a central concept in mechanism design theory. And the basic idea is that when we are trying to find optimal mechanisms which maximize some desirable goal, like maximizing team surplus, for example, over here, there is no loss of generality, according to the revelation principle, in restricting attention to truth-telling mechanisms which have this property that it's in the interest of the agent with private information to announce the truth, right? So we will exploit the revelation principle and confine ourselves to such truth-telling mechanisms. Now, we are trying to understand this in the language of mechanism design theory. You can also think of it as a signaling game. And the optimal mechanism that I will characterize here, the optimal transfer function, if you will, can also be generated by the separating equilibrium of a signaling game, right? We will arrive at the same outcome. Now, you may have, when you studied signaling games, like the Spence model, you may have studied it with a discrete number of types, like a high type and a low type. This is just an extension to a continuum of types. What is a type? A type is a leader who has learned a particular value of theta, right? So each realization of theta gives rise to a leader of a particular type associated with that value of theta. So here we have not two types or three types, we have a continuum of types, therefore, right? Now, in two-type signaling models or mechanism design problems, your incentive constraints are inequalities. You have constraints which say that the high type shouldn't find it optimal to mimic the low type, or vice versa. So with a continuum of types, we have a generalization of those inequalities. Essentially, the slope of the transfer function will be pinned down by our incentive constraints. In principle, we'll have an infinite number of incentive constraints. None of the theta types want to mimic any other theta type, but once we analyze that, it'll boil down to incentive constraints saying that the slope of our transfer function will have to have a particular value. So I'll show that to you in a moment. This transfer is a sacrifice by the leader, right? You can think of it two ways. You can think of the sacrifice as a gift to the other team members, that this is money or resources that he gives away to the others. Or you can think of it as something that he wastes, that he gives it away to charity or just burns it. It doesn't matter what is done, right? Who receives it is unimportant. In this sort of signaling kind of model, what really makes a statement credible is how much the speaker is sacrificing. Yes. Okay. So we'll assume equal shares for now, that each team member, including the leader, has 1/nth share of the output. You will soon see at the end of this that the equal shares will also be optimal if the whole thing is symmetric, if everybody has the same cost of effort. So suppose the leader announces that the team productivity has the value theta hat. So theta hat is the announcement. We are going to look at truth-telling mechanisms, right? So in equilibrium, followers will believe what the leader said. because the whole thing is constructed in a way that it's in the incentive of the leader to tell the truth, right? So once followers believe the announcement, each follower's effort choice is given by the standard optimization, maximization, which we have done before. So we can use that same formula. It's basically going to be theta hat, which is the claimed value of productivity, and the productivity which, the claim which followers believe, divided by n. Yes? So using backward induction, right, given the announcement theta hat, this is how how hard all the followers will work. And now we take a step back to the leader's problem. So the leader knows the consequence of every possible announcement that he can make. All right? And the leader will choose his announcement to suit his interests, to maximize his interests. And so therefore, this is the problem which the leader is solving. So let's understand this. The moment the leader makes the announcement theta hat, he has to pay the transfer which the mechanism specifies, right? So he has to pay T of theta hat. So that is subtracted. What is this amount? If the leader announces theta hat, each of his team members will work this hard, theta hat by n. You multiply that by n minus 1, that's the total team effort. You multiply that further by theta, that is total team output. And finally, you have to divide it by n to get the leader's own share of that team output, right? So this is how much the leader gets from the effort choices of others. The leader also chooses some effort of his own, so there'll be an additional term, but that additional term will be independent of what theta hat the leader has announced. And that's because of the additive production function, right? So the leader's problem is really separable, right? The leader has to decide what announcement he should make regarding team productivity, and he also has to decide how hard he himself should work, and one problem has nothing to do with the other problem, right? So this is the part about optimal announcements. So notice that theta hat as well as theta sits in this objective function, right? So part of the payoff of the leader is coming from his announcement and how what others believe about team productivity, and part of his payoff is coming from theta without a hat, which is true productivity. Yes. So if you maximize this, assuming an interior solution, you get the simple first order condition that T prime of theta hat should be equal to this expression. That's straightforward. This is our first order condition, right? So whatever theta hat satisfies this, so the leader learns a particular theta, that's a parameter as far as he is concerned, and he's choosing theta hat himself optimally, and that theta hat is optimal, which satisfies this equation. Okay. Now, as I said, because of the revelation principle, we can impose the condition that theta hat equals theta, right? We are trying to find an optimal mechanism which has the truth-telling property, because the revelation principle tells us that there will always be an optimal mechanism which has that property, right? Imposing the truth-telling property leads to no loss of generality in optimal mechanism design over here. So the final step after we have written down this first order condition is to impose the truth-telling condition, namely theta bar or theta hat equals theta, right? So once I impose that in this last equation, I get a differential equation, right? And the differential equation is very simple. The derivative of the transfer function is linear in theta, so therefore the transfer function itself will be a quadratic, right? Because we'll integrate. And so this is our solution. This is the solution. So we have pinned down the transfer function. So the transfer function, if it takes this form, it will have the property that the leader will have the incentive to announce the value of theta truthfully. Okay? And then the rest of the analysis that we had on the previous slide just ties together. One thing we can, for any differential equation, of course, there's a constant of integration when you're solving it. But that constant is zero over here, because if team productivity is zero, then nobody gets anything from putting any amount of effort. And so the leader will not want to sacrifice anything at all. So it's a natural endpoint condition that T0 equal to zero, right? So the constant of integration is zero. So this really is the full solution. Now, equal shares was optimal under full information, if you remember, right? When the effort costs are symmetric across the agents, the best vector of shares, which maximizes or reaches second best team surplus, is equal shares for everyone. Now here we assume that at the outset, but the assumption wasn't bad at all, because what we have found is that the leader can always convey information about theta fully to the team members through this transfer function, this sacrifice function. So full information is basically achieved endogenously before effort choices are made, and so therefore equal shares remain optimal even in this asymmetric information version of the model. Now, one thing you might say is that it's tough being a leader in this situation, because the leader has to make all these big sacrifices in order to convey productivity information, right? So it's a raw deal for the leader, you might say. But remember that the agents in this model have quasi-linear utility, right? So it's linear in money. So it's always possible for them to arrange ex-ante transfers so as to achieve any distribution of the team surplus that they want to achieve. So broadly speaking, if the leader is going to sacrifice high amounts in expected terms to play this game, then the team can always have an arrangement where when the team is formed, the leader is paid a fee and the followers contribute to that fee, right? And those fees and transfers are unconditional transfers. They don't depend on what team productivity turns out to be or how hard people work. So through that sort of lump sum transfers in the beginning, things can be, the distribution of the pie can be made equal, unequal, any way you want, right? So for example, whatever the expected transfer is T of theta, the expectation of T of theta, right? That entire amount can be collected upfront by the leader from other team members when the team is formed at that stage. Okay, so what happens under this leading by sacrifice that we just studied? Essentially, the disadvantage of asymmetric information, the fact that all these inexperienced team members who don't know the value of productivity and therefore cannot choose their effort level to suit team productivity, that problem basically goes away, right? Because the leader, through sacrifice, is able to convey that information to the remaining members. So when the Indian team goes to Australia to play a test series, and there's not much prospect of winning, Virat Kohli doesn't give very lavish gifts to the team members, to the rookies, and the rookies realize that there's not much hope for us. But on a series when Virat Kohli realizes that they can win if they work hard, he convinces others by giving them lavish gifts. And then these junior members realize that there is indeed a good prospect, otherwise the captain wouldn't be giving these expensive gifts to us, and that persuades them to work hard, to spend a lot of time in the nets and so on. Okay, let's now shift our attention to the other kind of signaling that might happen here, the other kind of leadership, which is leading by example. And this is the more subtle and the more interesting phenomenon that we can find here. So let's see how that goes. So here, let's give a little twist to the timeline of the model. The leader observes theta and chooses his effort first before others. And let's assume that other agents can observe the leader's effort in this case, right? So somehow the leader can make his effort choice visible to others, right? In some environments that may be possible, and we are allowing for that. So the leader learns about team productivity, then chooses his own effort based on that, and then the others get to see not the team productivity but the leader's effort choice, and then the others decide how hard they want to work, right? And then the team output gets realized. So that's the timeline here. Here, instead of assuming equal shares, let's say that the leader has a share S and the followers have the remaining shares divided equally among them, right? It'll turn out, as you'll see, that it may not be optimal to give the same share to the leader as the followers, right? But between the followers, no discrimination is of any use. So they have equal shares with each other, but the leader's share can be some S. At this point, we'll take S to be arbitrary. And in a few slides, we'll talk about what should be the optimal value of S, right? Right now, S is fixed. So, in order to convince others that the team's productivity has some value, the leader has to choose some effort level EL. Okay, so once again, we'll take this mechanism design approach and we'll use the revelation principle to restrict attention to truth-telling mechanisms, right? So again, theta is the true productivity. The leader wants to announce to the team that the productivity is theta hat, right? And theta hat may or may not be equal to theta. It'll be equal to theta only if the leader is telling the truth, okay? And the mechanism says that if the leader wants to make an announcement theta hat, then he has to choose an effort level EL of theta hat. So this is the effort choice function, and the mechanism will specify this, right? And remember, again, this is endogenous, right? We'll be trying to solve for this function, right? That is very much the part of finding the optimal mechanism. But as far as the leader is concerned, this function has been given to the leader, right? And the leader is strategically deciding what announcement to make. Now, again, we'll do backward induction, right? First, we will solve for the last stage, which is that the leader has made an announcement and now the followers are deciding what level of effort to choose. And that's the usual straightforward maximization that has appeared before. Essentially, it's the productivity, the team productivity as far as the followers believe, divided by the share of each follower, and the share of each follower is, given by 1 minus s divided by n minus 1. So the leader solves this problem, right? So we know the follower's reaction function, if you will. That's what's appearing in the last line of the slide here. For every announcement that the leader might make, this is how hard followers will work. And now you take a step back to the leader's optimization problem, right? The leader is trying to maximize his payoff by choosing his announcement strategically. So this is what he's maximizing. So let's understand this. The last term is very simple. It's the effort cost of the leader. If he wants to make this announcement, the mechanism says this is how hard he has to work. And this is the cost of that level of effort. So that is being subtracted. What is this? Well, if the leader puts in this amount of effort, which he needs to do if he wants to convince others that productivity is theta hat. So this is his own effort. And from the previous slide, we calculated what the followers' reactions are going to be, what their effort choices are going to be, and there's n minus 1 such followers. So this is the sum of the efforts of the followers, and to that we have added the effort of the leader. So this is the total effort in the team. that times theta is team output, and the leader gets S share of it, right? So this is how much he gets, his benefit, and this is his cost, okay? Now, if you write down the first order condition for this maximization problem, you get this equation, all right? Again, very simple. You have to do the substitution. You have to take that effort choice function of followers from the previous slide, plug it in, and then this is just a simple quadratic function which is maximizing, and that gives us this equation, right? So this is a differential equation involving the effort choice function of the leader, yes. And then as a final step, we impose the truth-telling condition, as I said. This is just as before, as in the case of leading by sacrifice, that you allow the leader to tell a lie, right? The leader at this stage is free to choose any theta hat. It doesn't have to be theta, but we want to construct the effort choice function in a way that it's in the interest of the leader to tell the truth, right? So once writing down the first order condition for the leader, we impose the theta hat equal to theta, the truth-telling condition, right? And that reduces the previous thing to this differential equation, and here is just a function of theta, right? Here, the announced value of theta and the true value of theta were both sitting there in principle. But now we have reduced it to a differential equation just in terms of theta. So this is a little more complex of a differential equation, and but it's not difficult to solve. So let me just skip to the solution of this differential equation. The solution takes this form, and you can look up your differential equation maths lessons to sort of see how exactly it goes. But let me just say that this is the solution to this differential equation on the last line, and it is basically of the form that the effort function has to be linear in theta, right, team productivity, with the coefficient k of s. The coefficient will depend on the leader's share because that's going to affect his incentives. So obviously the coefficient will depend on that. And if we assume equal shares, give the leader as well as the followers 1/nth of team output, then in that particular case we get this expression for the k coefficient, right? So let's assume equal shares for a moment, right, to understand what's going on here. So in the case of equal shares, this is the coefficient. The leader's effort choice will be given by this formula, this coefficient times theta, okay? And the follower's effort choice is just 1/n times theta, right, the old formula. Now the question is the leader in this case, where everybody has equal shares, does the leader work harder than the followers or not? And the answer is yes, indeed, the leader works harder. So it's simple algebra. You can show that this expression here as a function of n, this is always greater than 1/n for integer values of n, yeah, or for values of n greater than 1, or greater than 2 rather. You can further show that this coefficient is strictly less than 1, right? It'll never exceed 1. So what does that tell us? Remember the first best effort level. The first best effort level is, in this case, will be theta, right? It's theta by lambda, but we have assumed lambda to be equal to 1. So from the Holmstrom paper, we remember that the first best effort level is theta. So ideally, this coefficient should be 1, right? If we want to achieve first best, then the leader should put in an effort which is exactly equal to theta. But in a full information world where all this incomplete information is not complicating matters, where everybody knows theta to begin with, in that situation, the leader's effort choice will be 1/n times theta. So what this is basically saying is that in this particular situation, the leader's effort choice, when he's leading by example, is going to be less than his first best effort level, but is going to be greater than his second best effort level. He works harder than his team members, fellow team members, and he works harder than what he would have worked if everybody knew productivity to begin with, right? And so therefore, leading by example leads to, it doesn't lead to perfection, it doesn't lead us to first best, but it takes us closer to first best effort level as far as the leader's effort is concerned, right? And that is what creates the gain in social welfare, right? Social welfare is higher in this situation than in the full information case, where the leader's effort choice would have been 1 over n times theta, okay? Now, let's try to understand that better, right? Why is leading by example better than leading by sacrifice, right? Basically, there are two problems in the team. At the very beginning, when they start playing this game, there are two problems. One problem is an informational problem, that only the leader knows the true productivity, the followers don't. And as we saw right at the beginning, if that informational deficiency remains in the team, then the team's overall efficiency and surplus levels would go down, because the followers won't know what effort level to choose. So that's the first problem, this informational problem, that most team members don't know the true value of team productivity. The second problem is the problem that was identified originally by Holmstrom, which we saw in the last lecture, which is that because everybody gets a share of team output, their private incentive to work hard for the team is less than what is socially efficient, what is good for the team as a whole, right? So members don't work hard enough. That's the second problem. So both of these are problems for the team that they have to try and overcome to the extent possible. And what's happening in leading by example is that the leader is trying to solve the first problem by working hard himself, right? The reason the leader, this coefficient is greater than 1 over n, is that the leader has two reasons to work hard. One is that part of the fruits of his labor will come to himself, not the whole part, but 1/nth share of that will come to himself. That's one reason for him to work hard. But the other reason is to try and convince others that it's worth working hard. If you can convince others of a higher team productivity and they work harder, then part of the fruits of their labor comes to the leader, right? So the leader has these two reasons. One is the direct fruits of his own labor. The other is the persuasive effect of his labor, the fact that it increases the effort and productivity of others. Yes? So, so the leader tries to convey team productivity by working harder himself, right? So he's trying to mitigate the first problem of the two that I've listed. And the way he's trying to mitigate it also actually, to some extent, solves the second problem which the team has. Yes? So, in a sense, two wrongs here make a partial right. Two vices produce a virtue. So if the first problem wasn't there, the team would be less efficient, less productive. Yes? So when he had only one problem, the full information case, where the only problem was that the members don't work hard enough. Everybody knows the value of theta productivity, but they're just not working hard enough because of the team incentive problem, right? So there the team achieves a certain level of efficiency, which is less than first best. When you add the second problem on top of the first, ironically, things improve, right? And that's because the way the first problem is tried to be mitigated by the leader actually eases the second problem, right? The leader wasn't working very hard when there was full information. And now when he's trying to convey information about productivity, the way he tries to convey it is by working harder, right? So that to some extent reduces the weight of the second problem. So this is an example where, which is an illustration of a more general principle which we often see in economics. One version of it was captured in what is called the theorem of the second best, in a paper by Lipsey and Lancaster. They were talking of a different context. They were talking of markets, and the general idea in that paper was that, if you have a set of markets and one of them has a distortion, right? It's not perfectly competitive. Maybe there's a monopoly, there's some sort of regulatory barrier or what have you. The question is it then optimal to have perfect competition and free markets in the other n-1 markets? And Lipsey and Lancaster argued and showed through examples that the answer is not necessarily. So if you have a distortion in one market, you may want to have distortions in some other markets through taxes or subsidies or what have you, right? Because sometimes two vices may be better than just one vice. And it's that broad principle which is showing up over here. Now, let me also try and relate it to signaling models, right? In the signaling models that you study, often the message is that costly signaling can be socially bad. It may create deadweight losses, right? The agent who's doing the signaling gains, of course, from the signaling. That's why he's doing it. But in the process, there's losses imposed on others, and the overall social gain can be negative from signaling activity, right? So, for example, when companies spend a lot of money on advertising, right, a lot of resources are wasted, and nobody gets out ahead, and consumers experience higher prices, so it's a lose-lose scenario. But the equilibrium is such, individual incentives are such that you can get high levels of advertising in a market, in an oligopolistic market, for example. Now, in all those stories, the signaling activity itself is costly to society, right? It uses up resources. It's signaling in itself is a bad, not a good. Okay, so people are trying to signal, let's say, their wealth by throwing lavish weddings or through sort of wasteful expenditure. All of that is a waste. The difference here is that the signaling activity, what is the signaling activity? The signaling activity is the leader's effort level, right? That is actually a good. So when the leader tries to send a stronger signal, that signal, instead of being a cost to society and the group, is actually a benefit to the society or group, right? And that's why signaling, instead of reducing the surplus, actually increases it. So that's the overall idea. Let me just complete it by touching upon a few remaining issues, right? I will skip this slide. This slide says that you can always find a configuration of shares so that what the leader's effort is in this sort of separating equilibrium and this sort of mechanism is exactly mimicked by the followers, right? It's not terribly germane to anything. Let's get to the issue of optimal shares, right? So remember that in this whole exercise that we solved, we took an arbitrary value of S, right? We formulated some arguments with equal shares for leaders as well as followers, but in general, what we derived as the leader's effort choice function under leading by example, was for an arbitrary S, right? So this coefficient depends on S in this manner, but this S can be anything. And now you can ask the question, what is the optimal value of S? Okay. For example, will equal shares be optimal? And the answer is in general no. Yes. But we can easily solve for optimal shares. And here's the outline of that exercise, right? Once you fix S and divide the remaining 1 minus S shares equally among the followers, and you work out the effort choice functions of the leader as well as the follower, you can plug in those effort choice functions into the social expression for social surplus for the team, right? The total value, the first term is the total expected value of output. The second term is the expected cost for the team, aggregate cost. And this is the expected team surplus, expectation taken over all possible values of theta, right? And you can maximize this by choosing S accordingly, right? And here's a first order condition, and the optimal S star is defined by another differential equation. In the paper, what Hermalin does is that he picks an example where and so these results on this last slide, which is discussed towards the end of the paper, are not analytical general results. This is for some simulation, for some special distributions. But let's quickly take a look at them. Usually the leader's share is decreasing in N as the team gets bigger. There's a general need to thinly spread out the shares, and the leader is not beyond that need. It works out that if the shares are chosen optimally, the leader will always work harder than his teammates, right? And essentially that's coming from the fact that the leader has this extra reason to work hard, that the leader has a signaling benefit from working harder, which the followers don't have. So the leader ends up working harder even after the shares have been adjusted optimally. For small teams, in Hermalin's example, the leader's share is less than that of his teammates, but as the team size grows, the leader's share is greater than that of his teammates. In particular, one interesting aspect is that, as N goes to infinity, as the team becomes very, very large, follower shares converge to zero, right? 1 by N will go towards zero, so the followers' shares go to zero. But the leader's share stays bounded away from zero. Even for very large teams, according to these calculations, the leader gets more than 12% of the shares, right? And one can say that, one can perhaps somewhat adventurously sort of invoke this result to give some sort of maybe rationale for why CEOs of even very massive companies may have non-trivial share options as part of their compensation package. And the broad idea is that, in small teams, the leader will work hard to signal even if its shares are small. But when the team size gets very big, most followers free ride anyway, right? Their shares get minuscule. So transferring the shares back to the leader produces more bang for the buck for the team. Okay, so let me wrap it up. We have studied this sort of particular view of leadership, where what distinguishes a leader from ordinary members of the team is private information about productivity. The leader, through experience, insight, skill, whatever, has a better idea about the prospects of the team. Yes, and good leadership consists of trying to credibly convey this information, right? If the leader can convey that private information to the rest of the members of the team, then that will make the team more efficient, more productive than otherwise, right? And we have found that the leader can do it in two ways. One is leading by sacrifice, and the other is leading by example. Both ways successfully convey that information. But leading by example leads to higher levels of welfare, leads to bigger team surplus. In fact, it's surprising that if all team members were experienced and were informed about theta at the outset, relative to that level of welfare, leadership through example actually produces higher welfare levels. So if the team starts with less information and the leader is trying to spread that information among his teammates, they end up with a high level of welfare, right? And the reason is that the leader signals team productivity through a virtuous act. So, having given you a very serious perspective on leadership, let me end on a lighter note. As I said at the beginning, that leadership is a complex issue and it has many dimensions to it. We just looked at one important dimension. There's a saying which says that, some people were born great, some achieved greatness, and some had greatness thrust upon them. So, life is full of randomness, and sometimes leadership is attained by people by accident. And so, I'm going to show you a clip from Charlie Chaplin's Modern Times, which kind of brings this out. So, in this clip, what will happen is that Chaplin, who's a tramp, a vagabond, an unemployed person roaming the streets, suddenly gets catapulted into a leadership position of labor movement through very accidental forces. So let's just watch the clip.